Alright guys, so continue from our last lecture. We were on the topic of heat transfer between different objects. We had this example problem where you have a cold coin dropped into a warm coin being dropped into a cold beer, and the heat transfer is between the two objects. And eventually they're going to reach the same final temperature. Okay, the coin by losing heat going down in temperature, and the beer by absorbing the heat from the coin and raise its temperature. But eventually they reach the same final temperature. Okay, now for two objects, okay, this is how we handle it. But what if in an isolated system we have more than two objects? Okay, so here's our next example. 50 grams of water at 20 degrees Celsius is placed in a coffee cup. 48 grams of water at 80 degrees Celsius is then added to it. The final temperature in the cup is measured at 80, oh no, not 80. 47.8 degrees Celsius. Calculate the heat capacity of the coffee cup. Know that CP, specific heat of water, is 4.18 joules per gram per degree Celsius. All right, so now we have a question, we have a ton of numerical conditions in it, okay, and now let's try to analyze how do we do this. Yeah. So you have some cold water in a coffee cup. So this is 20 degrees Celsius, 50 gram. Okay, and then you had some hot water. .48 grams, 80 degrees Celsius, added to it. Okay. To the cup that contains the cold water. Now you have a lot of water together. Okay, and we measured the temperature of the water now is 47.8 degrees Celsius. Now, so these are the conditions provided, and we're looking for heat capacity C of the cup. All right, so first of all, how many things are involved in this reaction, in this process? Now, cold water obviously is your object 1. Hot water is your object 2. Okay, when you mix them together, of course, the hot water is losing heat and the cold water is gaining heat. That should be pretty obvious. Okay, but since we're calculating the cup, okay, and let's be specific, we're calculating heat capacity of this cup, okay? So the cup itself is object number 3. So you have 3 things that has involved in the heat exchange. Yeah. All right, so for the object number 1, change of temperature is final temperature 47 minus 0.8 minus 20.0. For your object number 2, your change of temperature is 47.8 minus 80. What about your object number 3? Well, it says cold water is placed in the cup. So delta T of the cup here is going to be the same initial and final temperature. Final temperature is 47.8 for everybody. The initial temperature of the cup should be the same with the cold water because cold water was in it at the beginning. Okay? Yeah. So each of these 3 things had temperature change and had absorbed or released heat during the process. Now, how do we do this calculation? Now, don't forget, for all your heat change problems you're going to deal with in this class, you have to have an isolated system or insulated system, okay? Because only within an insulated system you can stop worrying about, okay, what if I lose heat to the environment? No, the environment in this case with the insulated system don't exist. Okay, so all the heat transferred is between these 3 things. Q lost plus Q gain equal to 0. Okay, but you only have 2 things here in the equation. Now, you only have 2 different scenarios in the equation. Okay, any objects you have in the system, they either lose this heat or they gain the heat. Okay, but do you have to limit yourself to one thing losing heat or one thing gaining heat? No. For our situation, let's see who's losing heat. Hot water is definitely losing heat. Okay, anything else losing heat? You don't have anything hot anymore. Okay, so who's gaining heat? Cold water is gaining heat, that's for sure. But look at the temperature change of the cup. The cup has a higher final temperature than the initial temperature as well. So the cup is also gaining heat. Okay, so really, instead of writing it as Q loss plus Q gain equal to 0, you can also write Q of the hot water plus Q of the cold water plus Q of the cup together equal to 0. So whether you have 3 objects, 4 objects, 120 objects, as long as you are in an isolated system, this equation stands. Heat of everybody add up to 0. Energy will not be created. Energy will not disappear for no reasons. Energy is only transferred between the objects that you have in the system. All right, so once you establish this, now it's all about breaking each Q down to expressions using these conditions. Okay, so what do we know about these objects? Hot water and cold water are both water, and we know Cp of water, so obviously this should be M of the hot water, Cp of water, delta T of the hot water. For the cold water is mass of the cold water, same CP, delta T of the cold water. And then for the cup, okay, we don't have a CP, but we are looking for a C. How do we represent Q with C? Q equal to C delta T. So C of the cup, delta T of the cup, and delta T of the cup just happen to be the same thing with the cold water. So altogether, these things equal to 0. Now, then it's about plugging your numbers in. It's a long equation, but everything should be in place. Mass of the hot water, 48 grams, times Cp, 4.18 joules per gram per degree Celsius, so grams cancel. Now, delta T of the hot water, 47.8 minus 80.0 degree Celsius, so degree Celsius cancel, so you have joules. Mass of the cold water, 50.0 grams, 4.18 joules gram degree Celsius, times 47.8 minus 20 degrees Celsius cancel. Now, C of the cup plus C of the cup is what we wanted. Delta T of the cup is 47.8 minus 20.0 degrees Celsius. The total of that equal to 0. So essentially this is a number. This is also a number. And those two numbers together plus C cup, let's say that's our X, okay, times another number equal to 0. That's a pretty simple algebraic situation that you can solve. Okay, rearrange the equation. You find that your C of the cup, the heat capacity of the cup, 23.4 joules per degree Celsius. Okay, because these numbers combine to give you a joule unit, and X times degree Celsius equal to that. And the unit of the C should be joules per degree Celsius, which is what we know. Okay, heat capacity have unit of joules or calorie per degree Celsius. So, pretty good after you take your notes, after you watch the video. Now, pretty good chance or opportunity for you to later on when you study the notes cover up my solution, read the question again, think about what we did here, and try to solve this question on your own. And can you finish this calculation, set up this calculation, finish it, and get this result? Okay. Now, so really at this point, if with thermal properties provided, it doesn't really matter, okay, how many different objects you have in a given insulated system, okay? Within this system, everybody's total heat eventually, okay, equal to 0. And you can plug in your numbers, make sure your final temperature, initial temperature, your different thermal properties are in the right place, okay? And you should be able to set up an equation starting from this original equation of Q loss plus Q gain equal to 0 and do your calculation. Yeah. All right, so far, okay, everything that we did here, okay, on heat exchange, whether it's heat transfer between two different objects or the heat change of a given individual object, okay, whether we use Q loss plus Q gain equal to 0, or we use the equation of Q equal to MC P delta T, NC M delta T, or C delta T, okay. One thing you should notice is that there's no chemistry here. If you're dealing with one object, obviously you don't have a chemical reaction. And when we're dealing with 2 or 3 different objects, okay, we're not focusing on chemical reaction. This example is water and water. Okay, obviously no reaction. Last example was a coin and beer. Obviously no chemical reaction. So why do you stick a whole bunch of heat information where no chemistry is involved in a chemistry course? No. Because the reason of that is that what we learn here provide us with a way of trying to find out what kind of energy is involved in chemistry. And that is a huge subcategory of chemistry. Okay? So after we learned the heat transfer, the next thing we're going to be talking about here really involves some chemistry. And we call this part thermochemistry. Okay? Now, we have talked about this as we start the energy section. Okay? We said that a very, very important aspect of chemistry, huge reason why people study chemistry, is the energy involved in chemical reaction. Okay? Now you think about the energy resources that people are using right now. Okay? If you're using fuel, any kind of fuel, fossil fuel, whether it's coal, whether it's petroleum, okay? Now, at the end of the day, what do we use fuel for? We burn it. For what? We're supposed to get energy out of it. Burning gasoline in your car eventually providing enough energy to push your pistons and make your car move. Okay? And that is all chemistry energy. Okay? That entire process of gasoline burning and releasing energy to the environment is what we study in thermochemistry. Okay? And if you think about batteries, okay, we talked about it earlier that, okay, battery reactions are all redox reactions. Okay? Why can redox reaction be used as batteries? Number one, of course, it's because redox reactions always involve electron transfer. Okay? And with the electron transfer, if you make the half reactions happen on different electrodes and lead the electrons out through wires, and go back to the other electrode where it needs electrons, you got a full circle, closed circuit, and that's going to give you electricity. Okay? But the other reason is that all chemical reactions involve some form of energy. Okay? Yeah. And redox reactions, okay, involve energy loss or energy gain. Okay? And whatever reaction that involves energy loss, okay, eventually we want to try to see if we can get that energy and use it. Okay, if you're wondering, well, you told us all redox reactions can be made into batteries, and what if I have a redox reaction that's absorbing energy? Well, if the redox reaction you're studying is absorbing energy, then the reverse reaction of it is releasing energy. So you can always find an opportunity for a reaction that provide energy to the environment and try to use the energy involved. Okay, so energy involved in chemical reaction is the reason that we study thermochemistry. All chemical reactions involve energy change. Some absorb energy from its environment. Some release energy to its environment. And how much energy is involved in a chemical reaction? When I burn this much of gasoline, okay, how much energy is going to be produced during this process of burning? If I use copper zinc reaction, single replacement reaction as a battery, if this much of copper zinc is used during the process, well, how much energy is going to be released as electricity? Now, that you can see is an obvious important factor when it comes to study the energy side of chemical reactions. Okay. Now, first of all, the amount of energy involved in a chemical reaction. Okay, we have a new concept to describe it. We call it enthalpy. We use capital letter H to represent it. Okay, like potential energy, okay, enthalpy is a state function, which means you don't have an absolute value of enthalpy for a given chemical or given chemical reaction. What you can only study is during a process of change, how much energy is gained or lost. Okay, so although we have the definition of enthalpy as energy involved in chemical reaction, when we measure that, what we measure is the change. So we call it delta H. Okay, and whenever you think about delta H to a reaction, okay, is very much the same as Q, okay, the heat change to an object. Okay, an object could lose heat, and you would have a negative Q value. An object could gain heat, and you would have a positive value. Same thing for the reaction. A reaction could be absorbing energy from the environment, okay, and then you would say the delta H for that reaction is positive because you're getting energy. Okay, if a chemical reaction releases energy to the environment, you would see that the delta H being labeled as a negative value because you're losing energy during the reaction. Okay, yeah. And every chemical reaction is a process like this. Okay, the reason of that, very simply, if we label different chemicals potential energy on a reaction progress chart, you would see, okay, originally if you have some chemicals, let's say the reactants, that have lower potential energy, and later on you made some products, and if those products just happen to have higher potential energy, okay, then the energy difference between the reactants and products, okay, is going to be a delta H. And in this case, because your reaction have to absorb energy from the environment to lift your reactants to products, and this would be a process where you absorb energy. We say the delta H is positive for this reaction, okay? Or you could have a bunch of reactants that has a higher potential energy, and then it turns into products that has lower potential energy, okay? And in that case, you can say that my chemical reaction, okay, the delta H difference between the reactants and products is a negative value, and we're releasing energy to the environment. Okay, energy releasing process. So burning gasoline, okay, or discharging a battery all falls into this category, and we call it exothermic reaction. So energy releasing process is exothermic. Okay, energy absorbing process, okay, like photosynthesis of green plants, okay, like the charging process of a rechargeable battery, okay, absorbs energy from the environment. We call it endothermic reaction. Okay, and now absorbing energy, endothermic. Now, all right, so of course, now you can see in chemical reactions, the amount of energy released or absorbed during a chemical reaction is always proportional to the amount of the reactants used. The more reactants you use, the more energy it releases or absorbs. Okay, and now when you put the amount of energy, okay, absorbed or released during a chemical reaction, that information together with the balanced chemical equation, for example, we know that burning of natural gas, methane, with oxygen gas produce carbon dioxide and water. Okay, now, so we know this is the balanced chemical equation. Okay, but if I put a delta H together with it, and we say delta H naught or delta H standard is negative 127 kilojoules. Now, these two pieces of information together makes this equation a thermal chemical equation. Okay, and this means that if you have, now, the little circle here, the naught or the standard, okay, as we read it, means that if you have this many moles of stuff, 1 mole of CH4 reacting with 2 moles of oxygen, and ended up producing 1 mole of carbon dioxide and 2 moles of water, then you will be releasing, negative sign means an exothermic, releasing energy to the environment. You will be releasing 127 kilojoules of heat, okay, to the environment. Okay, so with a thermochemical equations, we can do a lot of things. For example, if you use, let's say, natural gas, okay, to heat up water in a pot, okay, knowing how much water you need to heat up to what temperature, okay, you can eventually calculate. And of course, if you want to include the pot, okay, you would also need to know some thermal properties of the pot. But if we have those data, okay, we can actually figure out, okay, to heat up this pot of water from, let's say, room temperature 20 degrees Celsius to boiling 100 degrees Celsius, okay, how much heat do I need? And once you know how much heat you need, you would be able to figure out, using a thermochemical equation, how much natural gas I actually need to burn to produce that much heat to heat up my water. So a lot of the commonly known chemical equations at this point, people already know. Okay, their thermochemical equation and means the energy involved in those chemical reactions. And if you search a chemistry index, okay, and for our textbook, if you search the appendices where it has thermochemical reaction data, okay, you can find a lot of chemical reactions that already comes with the delta H value. All right, so now how did we get these values? How did we get the delta H values for a given chemical reaction? Now you're going to need the stuff that you learned earlier in the heat part. Okay, if I can make a chemical reaction happen, okay, within an insulated system, okay, and if my reaction release heat, then stuff in my system would absorb those heat. If my reaction is absorbing heat, then the stuff in my system is going to provide those heat. Now, then I can calculate delta H, because now your Q loss plus Q gain can be written in a different way. Okay, delta H plus Q equal to 0 in insulated system. Okay, because again, now, although this time energy is coming from your chemical reaction, okay, or energy is provided to your chemical reaction, but energy is still conserved in an insulated system. So again, what happens in an insulated system stays in an insulated system. Okay, the total of all the energy exchange eventually equal to 0. Yeah. And how do we do that calculation? How do we deal with that process? Let's see that from our next example. Okay, so 50 grams of 1.0 molar NaOH solution at 20 degrees Celsius is mixed with 50, let's use milliliter since we have molar, milliliter of 1.0 molar HCl solution, also at 20 degrees Celsius in a coffee cup. Okay. Final temperature in the cup is measured at 26.5 degrees Celsius. If the coffee cup has heat capacity C equal to 23.4 joules per degree Celsius, and all solutions have density equal to 1.0 grams per milliliter, and CP 4.18, kilojoules per gram per degree Celsius. Calculate delta H of the neutralization reaction happened. All right, so now let's take a look at this. So you have, this looks like a very complicated question, okay, because you have so many different numerical conditions. Volume, concentration, mass, temperature, heat capacity, specific heat capacity. Now, and where do I start? Well, first of all, you're calculating the delta H for the neutralization reaction, okay? Oops. So let's write that reaction out. You have NaOH reacting with HCl, producing, you already know what it produces. If you don't, you're really in trouble. Water and salt, okay? And I had a chemical reaction, okay? Now, what happened? I have 50 milliliter of 1 molar 50 milliliter in 1 molar. Now, you don't need me to tell you that this obviously is not a limiting reagent situation, right? You have two reactants reacting with each other in a 1-to-1 molar ratio, and you have the same volume and same concentration, so you have the exact same amount, okay? This is a stoichiometric amount for both reactants. So at the end of the reaction, both of your sodium hydroxide is gone, and your hydrochloric acid is gone. Okay. So this one's definitely not about stoichiometry. Now, all right. So what else do we know? Now, we know that both of these two things have 20 degrees Celsius temperature. So this is a difference from what we had earlier in the insulated system and no chemical reaction insulated system situation. Because in that situation, you always need to have hot object, cold object, and don't forget, this time you also have a coffee cup. Okay, now it's given you a heat capacity, which means this guy can absorb and release heat in your system. Okay, and since the reaction was happening within the cup, and originally both of your two reactants is at 20 degrees Celsius, so you can be sure that your cup starts at 20 degrees Celsius as well. Okay, now, without the chemical reaction, if this is just water instead of two chemical solutions in this cup, do you expect heat exchange? The answer is obviously no. Everybody is at the same temperature. Nobody's cold, nobody's hot, nobody's losing heat, nobody's gaining heat. Okay? But in this situation, you actually have a final temperature, 26.5 degrees Celsius. What does that tell you? Your solution got hotter. Why? If there's no heat transfer during the process, how can my solution get hotter? Well, if they're just simply objects that has nothing to do with each other, okay, you won't have a hotter solution. The fact of the matter is, we admit that There is a chemical reaction going on, and chemical reaction, as we know now, always involve energy. So now let me ask you this question. Is this chemical reaction endothermic or exothermic? Okay, and you look at this, you go, well, the final temperature is higher, the initial temperature is lower. That means the solution absorbs heat. That is a endothermic reaction. And if that's how you think, I'd have to tell you that no, you're wrong. Okay? What do you mean I'm wrong? Solution absorbed heat, right? Yes, absolutely. The solution absorbed heat. Okay? But who provides the heat? If the solution gained heat in an insulated system, somebody lost heat, right? Who lost heat? Think about that for a second. Both of your solution are now in the cup. The solution is gaining heat. The cup is gaining heat. Who lost heat? You can't tell me that nobody lost heat, okay? Because then you are going to be the first person to rewrite, okay, the law of energy conservation. No. Well, so how you're going to explain this situation? If you say, well, it's not endothermic, well, think about this. That equation that we had earlier, we said in an insulated system where a chemical reaction happens, we can always have delta H plus Q equal to 0. Okay? For every object in the system, the two solutions and the cup, okay, if we view them as objects, all three of them absorbed heat. So the Q, and those are the only three objects in the system. So the Q is absolutely positive. And for you to make the energy conserved, for you to make the total equal to 0, what does that tell you about your delta H? If this is positive, your delta H must be negative. And if your delta H is negative, what kind of chemical reaction do you have? Of course, you have an exothermic reaction. Okay, and now let's explain this. I put the two chemical solutions together in the cup. The chemicals within them start to react, going through this neutralization reaction. Okay, and during the process, the reaction, because it's exothermic, is going to release a whole bunch of chemical energy. Okay, and that chemical energy is then absorbed by the solution and the cup. So although no other objects are providing energy or losing heat, okay, still the chemical reaction itself provide energy to the solution and to the cup. And that's why the temperature of the cup increase. All right, so now, how do I do this calculation? Now, obviously you want delta H. So that stays in the solution, in the equation. Okay, now, what else can I do? Well, let's think about a Q. Okay, although these are two separate solutions before you mix them. Okay, but once you mix them, okay, they're one big solution. Okay, the good thing is when we're trying to figure out a Q, when we're viewing the solution as an object, I don't have to worry too much about different chemicals, concentrations, moles, all that stuff. Okay, what I can view this big body of solution, I can view it as, oh, this is 50 milliliter plus 50 milliliters, so it's a total of 100 milliliter. Okay, but I have CP for the solution, so I really don't need milliliter, but this thing is 1.0 grams per milliliter. Oh, okay. So I really just have 100 grams of total solution. So I can do Q of the solution, and obviously I can do Q of the cup. Okay, so put them together, the total equal to 0. Delta H is what we want, which means Q solution and Q of the cup should both be numbers. Well, Q of the solution is M Cp delta T, and Q of the cup is C delta T. Okay, so let's see. Delta H should equal to mass of the total solution. We just calculated it. 100 grams times 4.184 joules per gram per degree Celsius times delta T, 26.5 minus 20 degrees Celsius, plus C delta T, 23.4 joules degree Celsius times 26.5 minus 20, same temperature difference for the cup, degree Celsius. And all that equal to 0. That is a number. That is also a number. So, of course, I can figure out my delta H. And the calculation gave me my delta H, in this case, is negative 2870 joules. Okay, or I'll write it in a more scientific way, negative 2.87 times 10 to the third joules. Or you could write it as negative 2.87 kilojoules, because kilojoules is 10 to the third joules. Okay, now, we talked about this is an exothermic reaction, and we ended up getting a negative result for delta H, which is perfectly sound, perfectly reasonable. And by figuring out how much heat in an insulated system that is absorbed or released, okay, while a chemical reaction is happening in the system, we can always do calculations like this and figure out. And actually, now, vast majority of the thermochemical reaction data that people have nowadays, okay, the original ones, okay, are done this way. Okay, we make a chemical reaction happen in a container, okay, usually with the existence of some solutions. We measure temperature change. We calculate how much heat energy is transferred from the reaction to the things in your container, okay, and with the thermochemical data of the container of the solution, then we can calculate and find out for this much of chemical reacting with each other, what is the delta H involved. This process of using, okay, object's heat and the insulated system to find out the delta H involved in a chemical reaction, this method is called calorimetry. Okay, calorimetry is a big branch of thermochemistry. This is how we find thermochemical data, okay, experimentally. And this cup that we used, okay, now, in a accurately set up calorimetry experiment, we use a much better insulator, a closed container with its heat capacity carefully measured, okay, previously known, okay, and this cup is acting as what we call a calorimeter. Okay, so chemical reactions delta H could be measured through calorimetry by making the chemical reaction happen in the calorimeter. Yeah. But once we got these regular delta H values of the given amount of chemical, okay, how do we turn this into a standard value that we can put together with the chemical equation? Because right now you cannot put, oh, delta H of this equal to negative 2.87 kilojoules. Okay, you can't do that and expect this to be a thermochemical equation. People are going to be confused because you used a little bit of chemical. Okay, if you change the amount of chemical, if you use 100 milliliter of the solution, if you use like a 3.0 molar solution, then your value of delta H is going to change. And when you have equation, thermochemical equation like this format, that number can change. Okay, so in our next lecture, we're going to discuss how to turn the delta H value into the standard delta H value. That's it for today, and I'll see you on Friday.